Compatibility equations. That's the number one thing students get wrong on mechanics materials problems, especially problems that have a gap. Everybody's wild imaginations just start going crazy and you come up with all sorts of, I don't know, just everybody heads in a different direction. So your TA Indiana, he's a pro at these sort of gap problems. He's awesome at threading his needles and getting hidden behind the couch. So we're going to show you how to write the proper compatibility equation, which is going to make solving this problem a lot easier than it might at first seem. So write out my givens and finds, and I'm looking for the temperature that's going to make it so that the two bars just barely touch. So that means this is not an indeterminate equation, right? An indeterminate equation is going to involve a lot of extra steps. But since they're just barely touching, this is actually one of the easiest versions of a gap problem. Oh man, your Indy is in just bliss right now. He loves these little like neck scratches. All right, so the main equation we're gonna be using is that axial deflection, the change in length, is alpha times length times the change in temperature, where alpha is gonna have units of distance per temperature. It's how much a material stretches as a result of a change in temperature. The compatibility equation is what we're going to use to actually define the physical relationship. It's how that 0.08 inches comes into play. There is no one single compatibility equation. The reason this is the most common mistake is that you can't just look up the compatibility equation. You have to invent this yourself just based on the picture. You have to look at the problem, read the statement, and figure out your own compatibility equation. Sometimes this is going to involve similar triangles. Sometimes this is going to be adding lengths together. This is some sort of geometric restriction on how your materials are moving or stretching. In this case, since we're given that the two bars just barely contact each other, the compatibility equation is that the changes in length, delta 1 plus delta 2, has to exactly equal 0.08, the gap in between them. So we can write out then the two equations for delta, right? Alpha L delta T, where I'm using the different value for alpha for each material, which I have to look up in a table. All right, your TA Indiana believes in you. He knows you can finish the rest of this on your own. So let's see if he's right. So we take these two, delta 1 and delta 2, plug them into the compatibility equation. So we're adding together delta 1 plus delta 2, set that equal to 0.08, and the only unknown in this equation is the final temperature. Rearrange and solve for T, 118 degrees Fahrenheit. Now, if the final temperature were, say, 140 degrees Fahrenheit, this would be an indeterminate loading problem. This would mean that the change in temperature is so large that the two bars are actually pushing into each other. They want to expand more than 0.08. And in that case, you would have to solve for the amount of stress inside each one. Like you'd have to solve for the stress at each wall to figure out how much each beam is essentially being compressed due to the compressive forces on either end. And in that case, the compatibility equation would still be the same, except instead of just delta 1 and delta 2, we would actually probably have 4 delta terms. The 2 deltas as a result of temperature, and 2 extra delta terms, NL over AE, as a result of the compressive stress. So essentially the 4 changes in length, 2 due to temperature, 2 due to stress, those would add to 0.08 if we were given a larger temperature. If this video helped you out and you want to help me out just a little bit, go ahead and hit the subscribe button. I know it's a stupid vanity metric that doesn't count for anything, but sometimes I'm vain too. I like to see that little number go up a little bit each time. I'll consider it a huge favor, and just have a great rest of your day. Good luck on your next test.